Hey everyone, welcome to another session of Ceerazzledazzle Physics. In this video guys, I'm going to be doing a revision video on the entire forces topic guys. So I'm going to be running you through the entire forces topic. So let's get started. 3, 2, 1, go. Right, so scalars and vectors. So there are two types of quantities. One of them is called a scalar and one of them is called a vector. A scalar has magnitude, which means size only, and a vector quantity has magnitude and direction. So it has a size and direction. Vector quantities can be negative and they have a direction, and that direction can be represented using arrows. Some examples of scalar quantities are going to be speed, distance, time and mass. They only have a value, they don't have a direction. Examples of vector quantities can be the velocity, displacement, force and acceleration. Don't forget force, it can be represented with an arrow, yes, for the direction. So all of these can be vector quantities. Contact and non-contact forces. So contact force, objects which are physically touching each other. And non-contact forces are going to be objects which are not physically touching each other. Some examples of contact forces are friction, air resistance, tension, normal contact force. So like friction, two things rubbing together, air resistance, you're traveling through the air, tension when you're pulling things, and normal contact force when you place an object, let's say on the surface, the force pushing upwards over here. Non-contact forces can be gravitational force. Yes, the way of gravity, let's say a moon's being attracted by a planet. Yes, they're not touching, but there's a force between them. Electrostatic, so two charged particles, let's say one's positive and that one's positive, there's a force between them. Magnetic force, don't forget, if you have a north pole next to another north pole, they will both repel each other. So these are all non-contact forces. Weight, mass and gravity. So first of all, mass and weight are not the same. Mass is the measure of how much matter an object has, and it's measured in kilograms. The weight is a force, and therefore it is measured in newtons. Your mass is the same wherever you are in the universe, so your mass will remain the same, but your weight will change depending on the strength of the gravitational field of that planet. In order to calculate the weight of an object, it's simply going to be the formula: weight is equal to mass times by gravitational field strength. W is equal to m times by g. Weight is measured in newtons because it's a force, mass in kilograms, and the gravitational field strength will be Newton per kilogram. And over here you can see I've got an object over here, and the weight's acting downwards right through the center. The weight acts along the line of action drawn from the center of mass of the object. That simply means that the weight is going to act downwards from the center of the object over here. The center of mass. So the center of mass is simply going to be the point at which all the mass appears to act. So if I give you this square, we can quickly find it by going along the axis of symmetry over here and over there. As you can see, they cross, and therefore the center of mass is going to be right bang in the middle over here. So for this one, it's over there, and if this one, you can see it crosses, so the center of mass will be in this point over here. So when you find the lines of symmetry where they all intersect, that's where the center of mass can be found. Resultant forces. Resultant forces is simply going to be the overall force acting upon an object. So over here, as you can see, I've got an object over here, this ball, and there are all these forces acting on it. Well, look, we've got 10 newtons to the left, 10 newtons to the right, 30 up, 30 down. Well, the horizontal ones will cancel out, and the top and bottom ones will leave a resultant or overall force of 20 newtons upwards over here. 30 minus 10, it's 20 upwards over here. And don't forget, forces, the length of the arrow indicates the size of the force. That's why the 30 Newton one is much larger than the 10 Newton one. Parallelogram of forces. So let's say we have two forces acting upon an object. Yeah, I usually try and explain it with like a dog, and there's two leads attached to the dog. And if you're asked to work out what is the resultant force upon the object if it's being pulled in two directions, you've got to construct the parallelogram of forces. So first of all, you take both of the forces and you shift one downwards over there. So this force goes down over here. The other force goes across over here. And then all you do is simply drop a line from one end all the way to the opposite end of the parallelogram over here. When you're doing this, you actually have to draw it to scale. So the length of this arrow must be of a certain size. And the size obviously indicates the value of the force. So when you're drawing it, you must use a scale diagram. It could be 1 centimeter represents 1 Newton. That is a suitable scale. Or maybe 1 centimeter represents 2 Newtons over here. So when you're drawing this, once you've done this, you've constructed the parallelogram, then you've drawn the resultant force in between. Yes, then you measure the length of the resultant force, and then from here, you can work out the value of the resultant force, obviously using your scale. And you may be asked for the direction. You simply have to measure the angle with a protractor and also quote it. Resolving forces. Resolving forces simply means splitting up forces into separate components. So let's say I've got a 5 Newton force over here, and it's drawn to scale, 30 degrees to the horizontal. If you're asked to resolve this, basically that means that you're going to split it into horizontal and vertical components. So over here, basically, you're going to use a scale diagram. Yes, don't use trigonometry, just draw a scale diagram. You simply drop a line across and drop a line upwards, and then you measure the length of the line, and using your scale, work out the value of the force. So there we go, we have now resolved this force of 5 newtons vertically and horizontally over here. So don't use Pythagoras or trigonometry when you're doing this, simply use the scale diagram. Resolving forces on the plane. Right, so let's say we have the object and it's now on a slant. Yes, it's on a slanted plane over here. If you're asked to resolve the force, which is pulling it down right now, which is 5 newtons, you now need to resolve this parallel and perpendicular to the plane. So basically, if I was you, I'd say construct a triangle over here. So look, we've constructed this triangle, and we can see that now, and don't forget the triangle is right angle triangle over here. This force pulling downwards is now, look, parallel to the plane, and this force over here is going to be perpendicular to the plane over here. So once you've constructed your right angle triangle, you're simply going to measure the length of this arrow and obviously use your scale to work out how much that force would be. And you do the same for the parallel component. So that's how you resolve forces on a plane. You do it parallel and perpendicular to the plane. Work done. The work done is simply going to be the energy transferred via forces. So work done is equal to force times by the distance moved along the line of action of the force. That simply means that if I have a force acting in this direction, I'm looking at the distance in that same direction. So work done, W, is equal to F times by S over here. Work done is energy, therefore it's going to be measured in joules. The force is in newtons, capital N, and the distance is in meters over here. And look, on the right hand side, I've got a simple calculation which you can pause the video and obviously go through it yourself. Power. Power is equal to the rate at which energy is transferred. Power is measured in watts. Yes, power is measured in watts. Power is equal to energy transferred divided by time taken, and therefore P is equal to E over T. That's the formula. Power is measured in watts, energy is in joules, time is in seconds. So make sure you get the correct units down. Also, you should remember that energy transferred is the same as the work done, so therefore power is also equal to work done over time. So power is equal to W over T, where power is in watts, the work done is a measure of energy, therefore joules, and the time is in seconds. And on the right hand side over here, you can see I've got another example. The relationship between force and extension of a spring. Right, so this is a simple practical that you should be aware of. So imagine I have a spring of length L, and we're going to look at how the extension of the spring changes as you add masses to the end of it. So when you add a mass to the end of it, first of all, it will have a final length F. To work out the extension, you do F minus L, that will tell you the extension, how much it is extended by. Then you would keep adding masses at the end of it. Obviously, it would extend more and more. So look at my table of results. First of all, I have the original length L, and then we're going to add the mass over here. Final length F. Therefore, to work out the extension, I'm going to do the final length minus the initial length that goes in this column over here. Then the force. Don't forget, I don't want to talk about the mass, I want to talk about the force. The force is simply the weight of the masses at the end, which is going to be mass times by gravity. That's this one over here. Then you repeat this, keep adding masses each time here, taking all your values. Control variables, use the same spring throughout the experiment. Risk assessment, wear goggles in case the spring bounces off and causes eye injury. And obviously don't put your feet underneath the masses. Errors, when taking measurements of the length, ensure that you are eye level with it, so therefore you reduce the parallax error. And then you should get the following graph of force versus extension. It should be going up initially. It may curve off at the end, but you should go up first of all and then curve off at the end. Force extension graph. So there are parts of the force extension graph you should be familiar with. The first one's going to be the limit of proportionality. I always call it LOP. It's the last point at which the force is directly proportional to the extension over here. The elastic limit is after the limit of proportionality. This is the point at which the spring, if you go beyond this point, it will not return back to its original length. But if you're up to that point, it will return back. So beyond the elastic limit, the spring will now become deformed. Before it, obviously the spring will return back to its original length. And then if you keep on adding masses, what happens is that eventually you'll reach the breaking point, which is going to be BP. We can call the left-hand side here, this region over here, the elastic behavior, and the right-hand side going to be the inelastic behavior, sometimes called the plastic behavior as well. Hooke's law. Right, so up to the limit of proportionality, we should recognize that force is directly proportional to the extension. Therefore, the force is proportional to the extension over here. Therefore, F is equal to a constant times by E. We're going to call this constant K, and that represents the spring constant. It's a measure of how stiff the spring is. The greater the spring constant, the stiffer the spring is. So looking at this, force is in newtons, extension in meters. The spring constant is Newton per meter over here. And look, if we're given the graph of force versus extension, if I was to work out the gradient, it's the change in y of the change in x. It's the change in force divided by the extension, which is going to be the spring constant k. The elastic potential energy. So the elastic potential energy stored in the spring. So if I was to add masses to it, hopefully you recognize it would have energy stored. What would happen is that we can work out the elastic potential energy using the following formula. It will be half times by the spring constant times by the extension squared. So there we go. E is equal to half ke squared, where E is in joules, the spring constant is still in newtons per meter, and extension is going to be in meters. Levers. So this is basically going to be the physics behind how a spanner works or how a wheelbarrow works. So look over here, we have a wheelbarrow, we've got a load on one side and effort on the opposite side. We've got a pivot point over here. The pivot point is where it rotates about. Right, so first of all, recognize that the greater the distance from the pivot, yes, the greater the force on the load. So obviously if I push from down below, I'll have less of a force on the load. So as I increase the distance from the pivot, the greater the force will be on the load to lift it up over here. And look on this side over here, we have a seesaw. So look on one side, I've put a load, it's pulling it down, but obviously to balance it out, I must push down the effort on the opposite side. And as you can see, because the effort is a greater distance from the pivot, obviously it has a bigger effect on the load. Levers are force multipliers, which means that they can produce a greater output force than the effort force applied. So therefore you might have a small amount of force there, but you can get a bigger force because your distance is greater. Moment. A moment is simply a turning force. The moment is equal to the force times by the perpendicular distance from the pivot. So over here we've got a pivot point and this is our beam. Moment is equal to force times by the perpendicular distance. Therefore force is in newtons, the distance is in meters, and therefore the moment is in Newton meter. Moments can either be clockwise or anti-clockwise. So in this case over here, we know it's going to spin the beam anti-clockwise. It's trying to drag it anti-clockwise over here, therefore causing the beam to turn. The principle of moments. So for any beam to be balanced, we need to have the following rule. The sum of the anti-clockwise moments must be equal to the sum of the clockwise moments. So that simply means that, look, in this example, we've got A, B, and C, 3 different loads on the seesaw. We can recognize that the moment of the anti-clockwise ones, which is the A, yes, that's anti-clockwise, trying to pull it anti-clockwise, will be equal to the moment of B plus the moment of C. There we go over here. So the moment of A is equal to the moment of B plus the moment of C. Therefore, F1 times by D1 is equal to F2 times by D2 plus F3 times by D3 over here. And therefore, this proves that the beam is balanced. Pressure. Pressure is simply going to be the force acting per unit area. P is equal to F divided by A, and that's going to be the area in contact with the table. Yes, let's say we have this box, the area in contact with the table, that's the force pulling down over here, that's my arrow. In terms of the units, the force is in newtons, the area is in meters squared, and the pressure will be measured in Pascal. But don't forget, 1 Pascal is the same as 1 Newton per meter squared. Gas pressure, so we talked about this in the kinetic theory video, which I've done previously, but we'll just revisit it again because obviously it's about forces. So number 1, particles inside a gas, they travel across, they collide with the walls of the container. Each collision, they exert a force. Because there is force acting per unit area, which is the walls over here, therefore there is a pressure. There is now a pressure over here. The pressure in a fluid. So right now, the pressure in a fluid, to work out the pressure in the fluid, it's equal to the density of the fluid times by the gravitational field strength of the planet that you're on times by the height of the fluid. P is equal to rho GH, where P is the pressure in Pascal, density is in kilogram per meter cubed, gravitational field strength is Newton per kilogram, and H is the height over here, which is measured in meters. That means the height from the top of the surface downwards, so that is going to be H in this diagram here. Atmospheric pressure. So here is the Earth's surface, and look, the air above the Earth's surface, usually we think about it as uniform density. Yes, equally spaced. But in reality, it's not. Gravity acts on all the particles, and it drags those particles down to the surface of the Earth over here. So therefore, as the altitude increases, as you get further and further up, the pressure decreases. And then we get the following graph, that pressure versus altitude. We can see that as the altitude increases, the pressure drops down. So the pressure is going to drop down. Because we're talking about a fluid still, we can still use the formula pressure is equal to density of the fluid times by the gravitational field strength times by the height of the fluid over here to do calculations about atmospheric pressure. Distance versus displacement. So now, distance versus displacement, so this is going to be scalars versus vectors one more time. So over here we've got an object A and it's trying to get to B. So first of all it moves 5 meters up, 6 meters, 4 meters and 9 meters. Total distance is the addition of them all, 24 meters. The displacement is simply the direct route from A to B over here. There we go, and measuring that distance over here. Obviously, because it's a vector, we're going to have to put the angle theta. So distance is going to be a scalar quantity and displacement is going to be a vector quantity because look, it does have a size and it now has a direction. The basics of motion. So first of all, you should hopefully identify that speed is equal to distance divided by time. Yeah, the speed of an object is going to be the distance divided by time. That's a scalar quantity. Velocity is the vector version. It's the displacement divided by the time. So we can have the following. V is going to be the velocity, displacement is s, time is in t over here. And look, velocity is going to be measured in meters per second because you're dividing the meters of a displacement divided by time in seconds. That's why it's meters per second. Couple of things you should be aware of is that the average walking speed is 1.5 meters per second, running 3 meters per second, and cycling 6 meters per second. The speed of sound is also 330 meters per second. Just make sure you're familiar with those values. Now, distance time graph. So over here we have a distance time graph. On the y-axis, I've put the distance, x-axis, I've put the time. Hopefully you can recognize that if it's a diagonal line, it means it's a constant speed. If it's a straight horizontal line, it means it's stationary over here. If I wanted to work out the speed, it's simply going to be the gradient of the diagonal line because it's the change in y over the change in x. And don't forget, on the y-axis, you're changing distance divided by time taken. Distance divided by time is going to be the speed over here. So just summarizing that, the gradient of a distance time graph represents the speed, and the higher the gradient, the greater the speed. Acceleration is simply the rate of change of velocity. So there we go, acceleration is equal to your change in velocity divided by time taken. That's the same as your final velocity minus your initial velocity divided by the time taken. And acceleration is a vector quantity, so it can have a size and direction. If it is positive, that means you're accelerating, you're gaining velocity. If it's negative, you're going to be losing velocity, therefore it's called deceleration. Right, so our formula is going to be A is equal to delta V divided by T. Acceleration is equal to delta V over T, and A is therefore equal to V minus U divided by T. In terms of the units, the top line over here is velocity because it's final velocity minus initial, it's still velocity, meters per second divided by second is the same as meters per second squared. And we have another formula which is going to be V squared is equal to U squared plus the 2AS. Make sure you're able to use that and rearrange that to make V the subject or U the subject, where V is going to be the final velocity, U is going to be the initial velocity, A is going to be the acceleration, and S is going to be the displacement. Velocity time graph. So right now I have a velocity time graph over here. First of all, we can see that if it's a diagonal line going upwards, you are accelerating because you are changing velocity. If it is a straight horizontal line, it's a constant velocity over here. And if it's going down, it's going to be deceleration going downwards. If I was to look at the gradient of this line, because the gradient of the line is the change in y over the change in x, it's the change in my velocity divided by change in time, which is the acceleration from before. So the gradient of a velocity time graph represents the acceleration. The higher the gradient, the greater the acceleration. So the higher the gradient of that line, the greater the acceleration. Okay, and also if I'm asked about the distance traveled for this journey, it is simply going to be the area under the line. So the area of a velocity time graph represents the distance traveled over here. You can either use the trapezium rule for the area, the half a plus b times by h to do that, where this is a, this is b, and the h is the distance between them. Or you can work out the area of this triangle plus the area of this square plus the area of this triangle over here and add them together to work out the total distance. Non-uniform motion. Let's say you're given a distance time graph and the graph is curved and you're asked to work out the velocity. Right, you can't do the gradient of the line because it's not straight, but you can use the tangent rule. So the point you're looking at, let's say you're looking at the time on this time over here, you start to construct a tangent at this point and then you work out the gradient of the tangent. So there we go, as you can see I've constructed a triangle and now I'm going to work out the gradient of this triangle. So the gradient of this tangent on the displacement time graph, it represents the velocity. So make sure that you're happy with that. So I can use the gradient of the tangent to work out the velocity from a non-uniform displacement time graph. Also, if I'm given a velocity time graph of non-uniform motion, look, the graph is curved, and I'm asked about the acceleration, I simply have to do the tangent rule again. So we construct the tangent over here, and once again, we'd use the gradient of the line because the gradient of the tangent on the velocity time graph will represent the acceleration because you're having the change in velocity divided by the change in time. Terminal velocity, let's talk about the forces acting upon a skydiver when they jump out of a plane. So initially the only force acting upon it is the weight pulling it down, and therefore the object accelerates. But as it falls down through the air, what happens is air resistance starts to build up. Yes, so the acceleration starts to reduce. It's still moving downwards, then eventually the air resistance balances out the weight. So when the two forces are balanced, what happens is the object will no longer accelerate, it will move off at a constant velocity. And this, the final velocity it reached, this is called the terminal velocity, because it's the final velocity it reached over here. Then, when the skydiver opens up the parachute, what happens is the air resistance increases dramatically. So the air resistance increases dramatically, and therefore the object starts to decelerate. You start to decelerate. And then finally, the two forces balance out again, and therefore the object starts to travel at a lower constant velocity. So yes, it's a lower terminal velocity at the end. Let's look at it in terms of a graph. So over here, guys, you can see that, look, we've got a velocity time graph. So initially, yes, the weight is acting and it accelerates, but as the air resistance builds up, the acceleration starts to decrease, hence why the graph is starting to level off. Then at terminal velocity, don't forget the velocity is not changing, that's why it's flat. And then finally, when you open up the parachute, we decelerate, and then eventually the forces balance out again with that lower terminal velocity over here. There we go, and finally you hit the ground. Newton's first law. Newton's first law states the following, that if the resultant force upon an object is zero, that means that the forces are balanced, the object will either remain stationary, yes, or move at a constant velocity. So over here, look, if the two forces are balanced, it's stationary. Two forces are balanced here, up and down are balanced, it's stationary. But we also just looked at when the two forces are balanced and it's still moving. But don't forget, it's moving at a constant velocity. So this is going to be Newton's first law. Newton's second law. Newton's second law states that if there is a resultant force upon an object, well, the object will accelerate. So look over here, we've got an object and it's got all these forces acting upon it. Hopefully you recognize that the resultant force is 80 newtons upwards. 100 minus 20, 80. Yeah, 50-50 cancel out. Newton's second law states that the acceleration is directly proportional to the resultant force acting upon it, provided that the mass is constant. And it also states that the acceleration of the object is inversely proportional to the mass of the object. So therefore, the greater the mass of the object, the lower the acceleration will be. So we have F is proportional to A and A is proportional to 1 over m. Combining them together, we get the resultant force, which is this symbol, sigma. F is equal to m times by A, where the force is measured in newtons, the mass is in kilograms, and acceleration is meters per second squared. Investigating the effect of varying the force on the acceleration of an object for constant mass. Okay, so this is quite a tricky experiment, but I'll walk you through it. Over here we have a trolley and it has a piece of string attached to it and it's hanging off the edge of a table on a pulley, and look, it's attached to some masses at the bottom over here. So what we're going to do is the following. We're going to take masses from the top of the car and place them at the end over here, and we're going to see how it accelerates through here. Right, we're looking at how the force pulling down, don't forget the force which is pulling down will be the same as the force pulling across, and how that affects the acceleration. We're going to keep the mass of the entire system constant by taking masses from the top of the car and placing them over here. That's how we're going to keep the mass constant. Right, so what is the data logger? The data logger is going to take some measurements for us. The data logger is connected to the light gate 1 and light gate 2 over here. As the car accelerates and goes across, it will go through the first light gate over here. As it goes through the first light gate, what will happen is the data logger will therefore calculate the initial velocity that will go into our table over here. Then as it goes through the second one, it will calculate our final velocity. Right, how are you going to work out the acceleration? You're going to also time how long it takes to move between this light gate and this one using a stopwatch. So therefore we can get the final velocity, initial velocity and time taken. We can work out acceleration as the change in velocity divided by time. How are you going to get the force? That's simply going to be mass times by gravity over here. And look, we've got our control variables. Keep the mass of the system constant by taking masses off the trolley and place them at the end of the mass hanger. The risk assessment is obviously don't put your feet under it. So therefore from here we can get the following graph. Force versus acceleration. We can hopefully see that the greater the resultant force, the greater the force acting on the end of the pulley, the greater the acceleration on the car. Second experiment, investigating the effect of varying the mass of an object on the acceleration produced by a constant force this time. So this one is slightly different. In the previous example, we were taking masses off and adding them to the end, therefore increasing the force. This time round, I'm going to keep the force the same, so I'm not going to change any masses at the end. So what we're going to do is we're going to take additional masses and simply add them on top here. So masses are added here only. They're not taken from anywhere else. So once again, you're going to add masses to the trolley over here and release it. Hopefully you will recognize that we're going to measure the initial velocity one more time, final velocity, time in between, and work out the acceleration. And the more and more mass you add on here, obviously if this force remains the same, therefore the acceleration would decrease. So the greater the mass on the trolley over here, the lower the acceleration should be. And the control variables in this experiment have slightly changed. We're going to keep the mass at the end of the hanger constant. The reason why is because we need a constant force pulling it downwards. In terms of the results, what should you obtain? You should obtain the following graph, that as you increase the total mass of the car, the more and more mass you add on top of the car, the acceleration will decrease. Don't forget, they are inversely proportional to one another. Yes, because A is proportional to 1 over m. Inertia. Inertia is the tendency of an object to remain in its existing state. So for example, if an object is at rest, it would like to remain at rest. If the object is moving at a constant velocity, it will want to remain at a constant velocity. All objects have inertia, moving or not. So there we go, we've got a stationary object. Yeah, inertia wants it to remain, not moving. And look, an object moving at constant velocity, it wants to remain moving at constant velocity. The inertial mass is simply a measure of how difficult it is to change the velocity of an object. The greater the inertial mass, the harder it is to change its velocity. The lower the inertial mass, the easier it is to change its velocity. To calculate the inertial mass of an object, we simply look at the ratio of the force over the acceleration. So m is equal to F divided by A, which is from Newton's second law. Newton's third law. Newton's third law states that forces exist in pairs, and if object A exerts a force on object B, then object B will exert an equal and opposite force upon object A. Here are two examples. So over here we've got an object just resting on a surface, therefore the weight of the car pulling down is equal to the normal reaction force pushing upwards. They're both balanced out. And here's a non-contact example. So as you can see, we can see that the Earth attracts the Moon, but also the Moon attracts the Earth as well. Yes, that's the reason why we have the tides. They're being pulled closer towards the Moon. Stopping distance. Stopping distance is the total distance travelled by the car, which is equal to the thinking distance plus the braking distance. Thinking distance. The thinking distance is the distance travelled by the car from the moment you spot the hazard until you apply the brakes. Don't forget, as you're thinking about it, applying the brakes, the car is still moving. It is affected by our reaction time and the speed at which you're travelling at. The braking distance is the distance travelled by the car once the brakes have been applied. The braking distance is affected by physical factors, not like the thinking distance. Over here, I have a simple diagram in which a car is moving, then comes to a stop over here. So initially, there's the distance travelled is going to be the thinking distance, the brakes are applied, and then it's the braking distance from here. But the total stopping distance is the addition of the thinking distance plus the braking distance as stated above. Factors affecting thinking and braking distance. Right, so these are the factors affecting the thinking distance, which is going to be alcohol consumption, intoxication of drugs, age, mental health, distraction, tiredness. Factors affecting the braking distance are going to be the condition of the tyres, condition of the brakes, friction of the road, and weather conditions. So look, all these ones are more physical. These ones are about the human reaction time. And over here, what is going to be the intersection? Speed is affecting both your thinking distance and your braking distance. So the faster you are, the greater your thinking distance and braking distance will be. Momentum. Momentum is simply how difficult it is to stop a moving object. Momentum is a vector quantity, therefore it has a size and direction. It can have a negative value. The negative value indicates the direction. Right, so momentum, the formula is equal to the mass of it times by the velocity. There we go, P is equal to mv. Mass is in kilograms, velocity is in meters per second, therefore the momentum is in kilogram meters per second. Over here we can work out the momentum of this to be 60 kilogram meters per second, but because I've taken going to the right as positive, going backwards this direction, it has to be negative. So look, the momentum of this one will be minus 120 kilogram meters per second because it's moving in the opposite direction. The principle of conservation of momentum. The principle of conservation of momentum simply states that the sum of the momentum before the collision is equal to the sum of the momentum after the collision. So that means all the momentum before should be equal to all the momentum afterwards. I'm going to walk you through multiple examples so that you can get your head around it. So in this example, I've got car A colliding with car B. Car B is stationary. But afterwards, when they collide, they stick together and they move off. Well, hopefully you can see that the sum of the momentum before is equal to the sum of the momentum afterwards. So the momentum of this plus momentum of this one should be equal to the momentum of both of them combined together afterwards. And look, if you check the maths, 20 times by 3 over here plus the 5 times by 0 should be equal to 25 times by the 2.4, it's 60 on both of them. Yes, momentum is conserved in this example. Alright, so this one is going to be a collide and separate scenario. So look, this one is going to be car A collides with B, but they don't stick together. They just keep on moving. So this is the before the collision, this is afterwards. So once again, the sum of the momentum before is equal to the sum of the momentum afterwards. So that means that the momentum of A over here plus momentum of B will be equal to the momentum of A over here plus this momentum B afterwards. So therefore it goes 20 times by 3 plus 5 times by 0 will be equal to 20 times by 1.5 plus 5 times by 6 over here, 60, 60, and look, momentum is conserved. Obviously they're all in the same direction, that's why all the values of the velocity are positive. Another example of the principle of conservation of momentum is going to be a collide and stop scenario. That means that two objects collide together and they simply stop moving. Well, look over here, we can say that sum of the momentum before the collision must be equal to the sum of the momentum after the collision. So here's before and afterwards. So therefore we can say momentum of A plus momentum of B must be equal to the momentum of this afterwards. Well, we know that it's not moving afterwards, so therefore the momentum of it afterwards is going to be 0 on the right hand side. The momentum of this one is 20 times by 3 plus 5 times by minus 8. Careful, but it's negative because obviously it's moving in the opposite direction. So therefore 40 minus 40, yes, it's 0 on both sides, and this is another example of the conservation of momentum still working. Last example of the conservation of momentum, this is going to be a cannon and cannonball explosion example. This is the one I always try and use to explain it. Let's say we have a cannon over here, A, and B is the cannonball inside. Initially it's not moving, then afterwards the cannonball flies off over here and the cannon moves backwards right now. So therefore we can still do the same thing. The sum of the momentum before the collision should be equal to the sum of the momentum after the collision. So the momentum of this before must be equal to the momentum of this afterwards. So initially it's not moving, so therefore the momentum on the left hand side is going to be 0, but on the right hand side I've got 20 times by 1, yes, plus 5 times by minus 4, yes, which therefore 20 minus 20, they both cancel out, and therefore the principle of conservation of momentum still works. Elastic and inelastic collisions. So in elastic collision, what happens is the momentum is conserved and the kinetic energy is conserved. In an inelastic collision, only the momentum is conserved and the kinetic energy is not conserved. The rate of change of momentum. So over here, let's say we have a bus of 20 kilograms and it's traveling and it comes to a stop over here. Let's say it comes to a stop in 2 seconds. We have another bus of the same mass, the same initial speed, and it comes to a stop in 100 seconds. In which scenario would you experience the greatest amount of force if you were inside the bus? Well, hopefully you recognize that it's going to be in the first one. Why? Because you change momentum in the shortest amount of time. So the rate of change of momentum affects the force experienced. So the shorter the time, the higher the force experienced for the same change in momentum. And the longer the time, the lower the force experienced for the same change in momentum over here. So now let's derive a formula for the rate of change of momentum. First of all, we should remember that Newton's second law, F is equal to ma. The acceleration is the change in velocity divided by time taken. We can plug that in, which is equal to mv minus mu, because don't forget v is final velocity minus initial. Therefore the force is equal to the final momentum minus the initial momentum, and we can therefore say this is the change in momentum divided by the time taken. So yes, force is equal to the change in momentum divided by time taken, and if we look at the graph of force versus time, we can see they're inversely proportional to each other. And airbags, crumple zones, cycle helmets, cushion surfaces on playgrounds all use this principle. They all increase the time of the collision to reduce the force experienced for the same change in momentum. Gears. A gear is a toothed wheel that rotates about their midpoint. So look, we've got two gears, they're round, they've got loads of teeth around them. And look, the small one is connected to the large one over here. We can see that as the small one rotates clockwise, the other one rotates anti-clockwise right now. The key thing to notice about the gears is that the force they have acting on each other is going to be the same, but they have different moments. Don't forget, both of them are turning, so they have turning forces. They will have moments within them. So we can then say that the force from gear 1 is equal to the force from gear 2. If you're wondering where the distance is in this, it's going to be the radius of the gear right now. So this is going to be d1, this is going to be d2 over here. We also should remember that a moment is equal to force times by distance, so therefore force is moment divided by the distance. So I can replace the force acting on the first gear is equal to m1 over d1, and the force acting on the second gear is equal to m2 divided by d2. Then just summarizing it all, that a small gear driving a large gear, let's say I have a small gear driving a large one, the small gear is going to rotate faster because it's smaller, it's going to be easier for it to make a complete circle compared to this one. The large gear is going to rotate slower. If the small gear turns anti-clockwise, the other gear turns clockwise. This one will have a smaller moment because it has a smaller radius, this one will have a larger moment produced. If we have a large gear driving a small gear, we notice that the large gear will rotate slower than the smaller output one. If the large one is going to rotate anti-clockwise, the smaller one will rotate clockwise. And you have a larger moment input and a smaller moment being produced from the smaller gear. And that's it for another session of Ceerazzledazzle Physics. If you're still struggling on the forces topic, why not check out my YouTube channel, in which I've got hundreds and hundreds of videos to help you with your studies, and I've broken the content down to small bite-sized chunks. Obviously, this is a revision video, that's the reason why I've done it quite fast, but don't forget you can rewatch the videos on my YouTube channel. Take care, ciao ciao and goodbye.